Welcome to Math 121. I'm Mr. Lewis, and this is the first video of the semester. In this video, we will be covering section 1.3. We will be covering a lot of material, so please don't hesitate to pause the video. To begin with, in 1.3, we want to talk about approximate numbers. What approximate numbers are and how they compare to what we call exact numbers. Also, we want to know how approximate numbers work with significant digits, which significant digits is at first hard to comprehend. A lot of people don't like significant digits, but if you can learn some very simple rules, it's not as bad as what people make it out to be. And using those rules, we'll be able to calculate accuracy, precision, rounding, and different ways of doing mathematical operations with approximate numbers. So first off, what is an exact number and what is an approximate number? An exact number is simply this: numbers that have been defined are counted. I can count that I have 10 fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is an exact number. I don't have more, I don't have less. It is an exact number. A day is defined as 24 hours. There is no more than 24 hours in a day. Sometimes we wish there is, but there isn't. Okay? So numbers that are defined or counted are exact. Approximate numbers are more of things that you have measured. Like I have a third cup of coffee or a third cup of water. I'm looking at it, but I'm making a guess. It's an assumption. Sometimes we might have a ruler and we're going to measure my foot to be 12.5 inches long, but the thing is, it's still an approximate answer because it's not entirely exact. What do you mean, Mr. Lewis? Because that makes no sense. I have a ruler. Well, here's the thing. No matter how you measure something, there's always this small amount of uncertainty, and so we have to estimate it. And that uncertainty is generally based upon who's measuring it. If you've never used a ruler before, you're not going to be good at measuring with a ruler. If you don't know how to use a graduated cylinder, you're not going to be good using it. Also, it could be like Mr. Lewis, myself, I have to have glasses. I might not be able to see the lines on a ruler as well as somebody who's got perfect 20/20 vision. All right, so let's look at this first example to kind of prove my point. We have like a little ruler here, and it's off in tick marks of 1 centimeter. Well, we look at it. We don't have everything exactly on 1, 2, or 3 centimeters. They're always in between. And so what we've got to figure out is what's A, what's B, and what's C. Well, when we look at A, we kind of can say, hey, that might be around 2.2 or 2.3 centimeters. But we don't know. We can't tell that for exact. We're making an estimate. The one thing we know for certain is that 2 is true. We just don't know about the 0.2 or the 0.3. So let's look at the next one. B, I think most of us would agree that's 3.5. However, even still, we may not be exactly right. Finally, C, it's about 4.1, maybe even up to 4.3. I really don't know. I am estimating, okay? Some of you may have said, oh, that's 4.2, but another person may say, hey, that's 4.3. So let's look at this next one. Notice that we're still in centimeters, but there's individual tick marks between the things. And so what we're actually counting now by is not by a whole centimeter, but by 1/10 of a centimeter. So in A, we can estimate this to be 0.23 through 0.24 centimeters. The only thing that we know for certain is that it's at least 0.2, but the 0.03, that last digit in the hundreds place, we're slightly unsure of. And it's the same thing with B, C, and D. Now D, we're a little bit more confident that it's exactly 3. But what if, just what if, that arrow was slightly to the left or slightly to the right? It's not exactly on the 3 mark, but it's close enough for us that, hey, we'll call it 3. This uncertainty where we don't know whether it says 2.2 or 2.3, we're going to call it a margin of error because we're human. And so that's what we're going to define that. So let's talk about margin of error a little bit more. In this course, I want to basically say margin of error is defined as plus or minus half the value of the last place. This basically means that whatever the last place value is, the margin of error would be half that. So if you were in the ones position, the margin of error would be half of 1. So it would be plus or minus 0.5, which is half of 1. All right. If the place value is in the 10th of position, half of it is 0.05. So your margin of error is plus or minus 0.05. Let's look at the examples and you might be able to understand it a little bit easier. Like the first number, it says 1.3. The last place value is in the 10th position. Half of 10th is plus or minus 0.05. So the least possible value that I can actually get is by subtracting that 0.05 from 1.3. And so my least possible value is 1.25. That's as small as it can go because we're just kind of, what if I didn't estimate 1.3 correctly? It could possibly be 1.25. All right. Now look at the highest possible value. It's adding 0.05. And so my highest possible value is 1.35. Even though my number says 1.3, that is what I'm estimating my measurement to be. It could possibly be as small as 1.25 and as large as 1.35. Okay, look at the next one, 142. The last place value is in the ones position. So the margin of error is by plus or minus half. So the smallest number I can get is 141.5. And the largest possible I could have seen is 142.5. And I estimated it to be 142. But it could be anywhere between 141.5 and 142.5. We're not really sure because of margin of error. So why don't you try the last two rows by yourself, pause the video, try them on your own, and then play the video again and see how you did. All right, significant digits. Basically, I like looking at significant digits are simply this. They're numbers that we consider important. All right, that's it. That's really about all we can really say about it. Significant digits are useful. That allows us to comprehend and communicate precision and accuracy of number, which we'll talk about here soon. But basically allows us to tell people our measurements, our numbers that we're seeing. It's just ways that we can make other people understand what we're doing. There are rules for identifying significant digits. So what I'm suggest you do is to pause the video here, and I want you to copy these down. Make sure you've got them, but I'm going to go through these rules. Rule 1, digits from 1 to 9 are always significant. Rule 2, 0 or zeros between two significant digits are always significant. Zeros at the right end of a decimal are significant. Zeros written as a 0 with a bar notation up top are significant. All right, now 5 and 6 are slightly different. Zeros at the end of a whole number are not significant, and zeros at on the left of a number are not significant. All right, now these rules right now make no sense to you probably, so the best way for us to do it is to look at some examples. All right, so let's check this out. First example is the number 1. All right, so what I want you to do is I'm going to do these first couple with you, is we're going to go down this list of rules and find out what applies. All right, first rule says digits from 1 to 9 are always significant. Well, is 1 between 1 and 9? Yes, it is. So that means that the number 1 is a significant digit. And since we only have that one number, the number of significant digits here is just 1. All right, now let's look at 20. All right, rule number 1 says digits from 1 to 9 are always significant. Therefore, we know the number 2 is a significant. So that's 1 that we can count. All right, now let's go down the rest of the rules. Zeros between 2 significant digits are significant. Well, is that 0 between 2 significant digits? No. All right, let's look at the next one. Zeros at the right end of a decimal are significant. Well, is 20, the 20 that I'm showing you, have a decimal in it? No, it doesn't. Okay, so rule 3 doesn't help us. Zeros written as 0 with a bar notation are significant. Does that help us in 20? No, it doesn't. Okay, so far we still only have 1 significant digit. All right, now look at 5. Zeros at the end of a whole number are not significant digits. Well, this 20 is a whole number, okay? And that 0 is at the end of a whole number. Therefore, the 0 is not a significant digit, which means that the number 20 only has 1 significant digit, okay? Let's look at the next one, 300 with a bar. Going through it again, 1 tells us 1 through 9 are always significant. So we know the number 3 is significant. So that gives us 1 significant digit. All right. Look at 2. Zeros between 2 significant digits are significant. Well, we're not sure yet. So the one thing we also know is if you keep going down to rule 4, it says zeros written as 0 with a bar notation are significant. So the 3 and the 0 at the end of this number, both of those are significant digits. So that gives us 2 so far. All right, so let's look at the 0 in the middle. Well, if you go back to rule 2, it says zeros between 2 significant digits are significant. We know the 3 is a significant digit. We know the 0 with a bar is a significant digit. Therefore, rule 2 states that the middle 0 is also. So altogether, we have 3 significant digits for number 300. One more, 1.06. We already know that 1 and 6 are significant digits. Okay, so 1 and 6 are significant digits. What about the 0? Well, rule 2 states zeros between 2 significant digits are significant. Therefore, that 0 is also significant. So altogether, we have the 1 is, the 0 is, and the 6. So we have 3 significant digits. Pause the video, try to do the rest of these on your own, and unpause and see how you did. Now, significant digits, when looking at a number in and of itself, just looking at a number, it's not so bad as long as you follow those rules that I just provided you. However, we have goes in a little bit more complicated here. First off, we need to look at what's called accuracy and another thing that's called precision. A lot of you may have your own definition for accuracy and precision. However, mathematics, especially in this class, we're going to be using different definitions, okay? So we're going to define accuracy is the number of significant digits that a number has. All right, so 1.05, based upon the rules that we just covered, we know that the 1 and the 5 are significant digits. Therefore, the 0 is also 1. So altogether, there are 3 significant digits. So 1.05 has an accuracy of 3 significant digits. All right, where 4.500, we know the 4 is, the 5 is, and then according to our rules, the zeros at the end of a decimal, which is what this is a decimal number because you see a decimal, those zeros are also sig figs. So altogether we have an accuracy of 4 significant digits. All right, so accuracy is the easy one. It's just counting the number of significant digits. Precision is a little bit more complicated. All right, it is the decimal position of the last significant digit. It is also considered the least precise digit due to margin of error. All right, so let's look at 1.05 again. The last significant digit is the 5. All right. Therefore, the precision of this number is to the 100th place because the 5 is in the 100th position. Also, this tells us that the 100th position is the least precise. You remember how in the video we could say that 1.05 there's that plus or minus margin of error, so that 0.05 could possibly be 0.055 or 0.045. Okay, so that's why it's saying that that last digit of the number is the least precise, even though it is the whole number is precision to the 100th place. All right, let's look at the next number, 4.500. All right, the last significant digit is the final zero of the number, and that is in the thousandths place. And because it is the last significant number, and it's also the least precise. So let's kind of do some together. It might help you out. I've got the rules written up here for you so you can see it, and let's check them out. So you have the number 0.12. All right, remember, accuracy is just the number of significant digits. So we know that the 1 is, we know the 2 is a significant digits. And then the 0 at the beginning. According to our rules, significant digits, the 0 at the beginning of a number, not just a decimal, not just a whole, but any number, the 0 at the beginning of a number is not a significant digit. Therefore, the accuracy of 0.12 is 2 significant digits. All right. The precision, well, the last significant digit in 0.12 is 2. So the precision is to the 100th. Okay. 140. Okay. We know 1 and 4 are automatically significant digits. The 0 in this one is seen at the end of a whole number. And since the 140 is a whole number, that 0 is not significant. Therefore, we can say the accuracy of 140 is 2 significant digits. The precision is based upon the 4 because the 4 is the last significant digit. Therefore, it's precise to the 10 spot, to the tens pin, not tenths, to the 10 position. All right, pause the video, try these other ones on your own, and then press play and see how you did. When rounding, there's some good things to remember. First off, when you are rounding a digit, you always look to its immediate right. And if that number to the right says 5, 6, 7, or 8, the number you're rounding goes up. If it says 0, 1, 2, 3, or 4, the digit you're rounding stays the same. And all the digits to the right of what you were rounding automatically get turned to 0. And if there are any decimals that are zeros, they generally get dropped. So like in this first number, when we look at it, it says 1.254. And since we're going to be rounding to the 10th, we're going to be looking at the 2. So the 2 is in our 10th spot, and we are to look at the right, which is our 5. This 5 tells us to round that 2 up to a 3. So we do. And we get 1.3. But the numbers 5 and 4, they are changed and rounded to zeros. And then finally, in our last little step, it says any zeros at the end of a decimal are dropped. So we can simply say that 1.254 rounded to the nearest tenth is just simply 1.3. Now, let's look at the next one. We are to round this to the nearest hundredth. So we need to look at our hundredth position. In this case, it happens to be 5. So we look to the immediate right, which is to 4. That 4 tells that 5 to stay the same. So our number will be 1, 2, 5. But that 4 becomes a 0 according to our rules. And then finally, according to our rules, all zeros at the end of a decimal are simply dropped. So we can say that 1.254 rounded to the nearest hundredth is 1.25. Now, this next one is asking me to round our number to 2 significant digits. So we need to look at our number. Well, if we look at it, we notice that we have 1, 2, 3, 4 significant digits. And what we are supposed to do is round to the second significant digit. And in this case, it happens to be the 2. Well, just like before, when we round, we're going to use that 5 to round the 3 up, and the 5 and the 4 change to 0, and we end up getting 1.3. Now, in the next one, we are rounding to 3 sig figs. So we're going to look at the third position. So 1, 2, 3. The third significant digit is 5. So we're going to round the 5. And just like we did in the hundredths position, it's going to be the same way. It's going to round to 1.250, or we simply say 1.25. Now let's do something a little bit more tougher. Let's look at this bottom one here. It says 121.129. Let's work at this one. All right, so we are being told again to round to the nearest tenth. So let's do that. Our 10th spot is this one right here. Okay, so this 2 tells that 1 to stay the same. And so what we end up getting is 121.100, because this 2 and the 9 become zeros. However, since these zeros are at the end of a decimal, we can just simply say 121.1. Now, we're now asked to do to the hundredth. The hundredth position is here. So this 9 tells that 2 to go up. So we now get 121.130, because the 9 turns into a 0. Since this 0 is at the end of a decimal, we can simply write this as 121.13. Now, our next one says two significant digits. So we need to look at our significant digits. When we look at this, we have 1, 2, 3, 4, 5, 6. So we are trying to find this rounded to the second significant digit. In this case, happens to be the 2. So this one tells that 2 to stay the same. And when we do, we get 1, 2. This 1 becomes a 0, our decimals, and the 129 also becomes zeros. Now, because these zeros are at the end of the decimal, we can simply drop them and easily just say that 121.129 rounded to 2 significant digits is simply 121. Now, let's look at 3 significant digits. And in this case, the 3 significant digit is in this position, the 1. So the 1 here tells this 1 to stay the same, and everything else becomes 0. So we get 121.000. When we look at this, the zeros get dropped, and we can simply say that 121.129 rounded to 3 significant digits is 121. Now, pause the video and try to finish the remainder of this on your own, and then unpause it and check your answers. I do need to caution you about one thing when you are rounding. Do not drop zeros that are significant. This doesn't happen a lot. Most of the time your rounding will be kind of like in the previous slide that we just talked about. However, sometimes you're going to get some weird numbers where you'll have some zeros that you just don't know what to do with. So let's take a look at this. 1.030 is telling us to round to the 10th. So this 3 tells the 0 that's in the 10th spot to stay the same. So when we go to round, it just becomes 1.000, okay, based on our rules. And now, previously, I told you that any zeros at the end of the decimal are dropped. However, this is one of those rare cases that's not entirely true. Because we were rounding to the 10th, that means that the 10th position is significant. So instead of writing the answer as just 1, we have to write the answer as 1.0. And it's only because we were rounding to the 10th. Now, let's look at rounding to the 100th. We know that this 3 is going to stay the same because of this 0, so we're just going to do it like normal. It's going to be 1.03. So no problems there. All right, let's look at the next one. We're rounding to the 10th again. So the 0 in the 100th place is telling the 0 here to stay the same. So we do it like normal. 34.000. And since we were rounding in the 10th place, that means that that 10th position is significant. So we can't get rid of that 0. However, these other zeros are not significant. So we could say this one to be 34.0. And now let's look at the 100th. When we round it, we would get 34.00. Now, these two numbers look the same to us. We're told that 34.0 and 34.00 are just 34. And in all intents and purposes in the real world, that may be true, but because we are rounding to a certain precision, this 34.00 is more precise because it's going to the 100th position versus this 34, which is only going to the 10th. All right, so let's finish this last one out together. All right, so we're going to round to the 10th again. So this 9 tells this 9 to go up. And because it's a 9, it can't go up but to only one number, and that's 10, which causes this number to also go up. And so what we end up having is 20.000. Okay? Now, same rule applies. Since we were rounding to the 10th position, the 10th position is significant. So our correct answer is 20.0. Now, if we were rounding to the 100th, this 6 tells that 9 to go up, and when it does, all the other 9s in front of it also have to go up. So we get that exact same number again, 20.000. But this time, since we're rounding to the 100th, our correct answer is 20.00. When working with approximate numbers, it's oftentimes before you start trying to plug numbers into the calculator and trying to do everything that you normally do, sometimes the best thing to do is to get an estimate of what your answer may be and save you a little bit of time in trying to get things accomplished. And one way we do that is when we see all these numbers like 12.97 plus 1.2393 minus 1.243, we can't really add that up and subtract all in our head. So what we do is we take an estimate, and the best way of doing that is round everything to one significant digit. So the number 12.97, when we round that to just one significant digit, we just get the number 10. All right, and then we are going to round the next number, 1.2393, to one significant digit, and we just get 1. And then we do the same thing on the last number, and we get minus 1. Well, this is something we can do in our head. So 10 plus 1 minus 1, and we find out that our answer should come out to around 10. So if we were to put this number in our calculator, put this a little expression in our calculator, and we found out our answer was 28 point something, and our estimate said 10, it means that something went wrong, and we probably need to check our calculator calculations, because more than likely we pressed a button wrong. So let's look at example 2. Again, I am not able to do this 0.380 minus 0.0460 divided by 1.945 in my head. However, I can round to one significant digit. So 0.0380 we can just simply say as 0.04. And we can say this top number, which is my numerator, to be 0.05. And then our denominator can be simply 2. Well, this is something that we can do in our head. We know that the next part is going to be 0.04 minus 0.025. And now we can even go farther and subtract this and say that 0.04 minus 0.025 is simply 0.015. So what this tells us is before we even put this expression in our calculator, our answer should come out close to 0.015. If we ended up getting a whole number after we put this in our calculator, we would know it is wrong, and apparently our fingers decided to be stupid and pressed the wrong buttons. This is one way of us checking our answers. So estimating an answer is good and all. However, it's still going to come to a point where you need to solve a problem, and you're going to have to take your answer and express it in either the proper precision or the proper accuracy. And that's all depending on whether you're adding, subtracting, multiplying, dividing, whether you're working with exact numbers or estimated numbers or all these other wonderful things. So what I suggest you do before we tackle that is you need to write down these rules. These rules are going to help you at the very end. So let's talk about it just real quick. When you add or subtract, once you're done with all that, you just simply round your final answer to the precision of the least precise number that you were working with. Right? Well, it's not that bad. We'll talk about that here in just a minute. Let's look at the next one. It says, when multiplying or dividing, the answer is expressed with the accuracy of the least accurate number. Again, I know your brain might hurt when you read that, but don't freak out. It's not that bad. So chill. Chill. All right. 3, finding the root, the answer is expressed in the accuracy of the number. And then finally, 4, when calculating the results between an exact number, such as 10 fingers, that's an exact number, and an approximation, which is 12.57893345, you're going to express your answer based upon the approximate number. Okay? So, pause the video. Make sure you write these instructions down, the rules down, and we'll come back and we'll look at these, and you'll see that it's not nearly as bad as you're expecting. So, I've got an expression down at the bottom, and we're going to use these rules to basically solve it. These rules are not that bad because the only thing that you really have to do first is simply put this expression in your calculator. All right? You literally put 12.78 plus 1.0495 minus 1.633 in your calculator. And when you do, you find out that you get this number, 12.1965. So we find out that this expression, when we add it up and subtract everything in our calculator, we get 12.1965. However, we know that these numbers are what we call approximate numbers, so we're going to have to do something with them. We can't just write this number on our paper or wherever we're going. We're going to have to round it. So what we have to do is we need to know what was the last operation we did. Well, if you know your order of operations, you know that you would do addition first and then you do subtraction last in the problem. So what we did was subtraction. So we look at our rules. It says when adding or subtraction, the answer is expressed with the precision of the least precise number. So what we're going to do is we're going to look at all these numbers and find out which number is the least precise. Well, this number, 12.78, its precision is to the hundredth place. Okay, it's to the hundredth. This position is to the this is the tenths, the hundredths, the thousandths, the 10,000ths. Well, this is a very precise number. When we look at this number, we have tenths, hundredths, thousandths. So this is a precise number. The least precise number is 12.78. And what it's telling us is that we're going to round our final answer to the hundredth position. So we look at our answer, 12.19, and we're going to round it to the hundredth position. So this 6 tells that 9 to go up. And when doing so, it causes the 1 to go up as well. So we find out that this number comes out to be 12.2000. Now, remembering our rules dealing with rounding, generally we always get rid of the zeros at the end of the decimal. However, we were rounding the hundredth position, so this 0 is important. So we cannot drop that. However, what we can drop is the remaining 2. So our final answer is just going to be 12.20. Just with like the last expression, in order for me to solve 3.64 times 17.06, all I simply have to do is plug this into the calculator. And when I do, I get that this is equal to exactly 62.0984. Now, since I was multiplying, I need to look at rule 2. It says when multiplying or dividing, the answer is expressed with the accuracy of the least accurate number. So I need to look at my numbers that I began with, and I need to look at the accuracy. Remember, accuracy is just basically how many significant digits a number has. Well, this number has, we know all 3, 6, and 4, all these are sig figs, so this has an accuracy of 3. Whereas when we look at this one, we know 1 is a significant digit, 7 is, and 6 is. And based on our rules on significant digits, the 0 is also a significant digit because it's between 2 known significant digits. So 17.06 has an accuracy of 4. Now our rule just simply states that we use the least accurate number. So the least accurate is 3. So we're going to round this to 3 significant digits. So 1, we know that's a sig fig. We know this is a significant digit. And we know this is a significant digit. Now, this 9 tells that 0 to go up. So when we do that, we find out that we get 62.1, and then we have zeros for the remaining of the numbers. Now, since we know that we were only rounding to the third significant digits, which in this case happens to be in this position here, these zeros are not needed. So our answer is simply 62.1. This expression should look very familiar to you. We were discussing it earlier when we were speaking on estimation. We estimated that this expression would have come out to approximately 0.015. So I want to see how close we actually were. So when we plug this into our calculator, we find out that the exact answer is 0.01156 and a bunch more numbers. I'm not going to work it all the way out, but you can see that we were very close. So our estimate was pretty accurate. So we can compare our estimate to the exact answer, and we can say, hey, our exact answer is right. All right. However, we need to round this to the appropriate precision or accuracy. So we need to look at it. In this problem, we both have subtraction and division, so we have to decide whether we're going to be following rule 1 or rule 2. We can't do both. So in order to do that, we need to understand our order of operations. Order of operations states that one of the first things that we always do is division first. So in this problem, we would divide first, and then after we divide, we would lastly subtract. This means that the last operation that we did is subtraction, and because that was our last operation, we're simply going to follow rule 1, and it says we're going to go to the precision of the least precise number. Well, the precision of this is to 1, 2, 3, 4 decimal places, or to the 10, hundreds, thousands, 10,000s. Well, this one's also to the 10,000s, while this one is just to the 10, hundreds, and thousands. So the least precise number is here. So we are going to round our answer to the 10, hundreds, thousands position, which is here. And when we do, we get 0.012, and then everything that follows it are zeros. But do we need those zeros here? No, we don't need those zeros because they are not significant. The only significant digit that we have to make sure we don't erase is this 2. So all these zeros are not necessary. So the answer to this expression when answer to the correct precision and accuracy is 0.012. This expression, again, looks tough, but as long as you know your order of operations and how to put this in the calculator, it is not a problem. So the first step into solving this expression and is finding out the correct answer is simply putting it into the calculator correctly. And when we do that, we find out that our answer just simply becomes 5.86781, and then a bunch more numbers that I'm not going to write. So 5.86787 whatever. And sorry for my sloppy handwriting here, but that's okay. Now, here's our exact answer. However, we still need to figure out how are we going to round our answer. Well, knowing our order of operations, we always do our multiplication and our division first. So when we do all that, what's left is just simply the subtraction. So the last operation that we do in this expression is subtraction. So we will follow rule 1. We are going to round the answer and express it to the precision of the least precise. So let's look at each individual number. This precision is to the tens position. This is also to the tens position, while this one is to the 10, hundreds, thousands position. This one is to the tens position, and then this last one is not but to the 1 position. All right, so the least precise number is here because it is in the 1 position, while everything else is either in the 10th or in the thousandth. Now, that basically means we're going to round our final answer, 5.867871, blah, 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 to the nearest whole number, and we can just simply say that this is going to be the number 6. So, this expression, when solved and expressed to the correct precision, is just 6. Here's the last example I want to talk about. This one you have to be very careful on. It gives you a little bit of instructions with the problem. It says perform the indicated operation, but then it tells you that the first number is an approximate number and the second number is exact. All right, that's really a key point here because it's going to help us when rounding at the very end. So in this particular problem, all we nearly simply need to do is add the numbers together. And when we add 0.970 plus 15.2, we get the number 16.1707. All right, now we need to round this. So we need to look at this last rule. It says when calculating the result between exact numbers and approximate numbers, the results are limited only by the approximate numbers. So we just need to look at the first number because the first number is approximate. So according to this, we are adding, and we're going to follow rule number 1. When adding or subtracting is expressed to the precision of the least precise number. Well, in this case, the least precise number is 0.9707. Even though this is only going to the tens, hundreds, thousandths, 10,000th space, and this is only going to the 10, this number is exact. We know this to be true. It is absolute. It is just like our 10 fingers. It has been counted and we know this to be true. However, this number is approximate. So we have to round it based upon this number and not the 15.2. Okay, so when we do, our precision is to the 10, hundredths, thousandths, 10,000ths, and so our answer is just left the same because it's already in this format. Okay, so be very careful. Always make sure that when you're doing your homework, read the directions because it will throw you a curveball like this. It will tell you sometimes the first number is approximate and the second number is exact. And if that's the case, you follow what the first number tells you to do, whether it's going to be adding, subtracting, multiplying, or dividing. So that completes section 1.3. I know that was a long video. It's come out to almost be an hour. Sorry about that, but there was so much information I feel like you needed to know. However, if you're still having trouble with any of the concepts that we covered in 1.3, please don't hesitate to email me or speak to me in class. Don't forget that you need to do your homework. You have to make a 70 or higher on each and every homework assignment in order for you to take a test. Don't forget that. It's very important. Again, sorry for the long video, but I felt like it was really needed so that you had a good, thorough understanding of things. Again, don't hesitate to email me or talk to me in class. All right, see you soon.